Welcome! In the world of self-driving cars, you might think the biggest dangers come from parts that break. But what if I told you the real mystery is how a system that's working perfectly can still be incredibly unsafe? Today, we're opening the Safety Detective's casebook to crack this exact code.
So let's just start with that central question, that paradox that keeps automotive engineers up at night. How can a car's safety system, with every single sensor and line of code working exactly as designed, still put you in harm's way? Well, the answer isn't about malfunctions. It's all about limitations. And that's the mystery we're going to unravel.
All right, first up, let's dive into this idea of the perfect systems flaw. This is a huge shift in how we think about safety. We're moving beyond the simple idea of if it's broken, fix it, and into the much trickier territory of understanding the built-in boundaries of the technology itself.
You can think of modern car safety as having two sides of the same coin. On one side, you've got traditional functional safety. This is all about what happens when things break. A sensor fails, a wire comes loose. But on the other side, there's SOTIF, and this deals with a much more subtle, sneaky problem. Hazards that pop up because of a system's performance limits, even when nothing is broken. The perfect example? A camera working exactly as it should, but it gets blinded for a second by intense sun glare. The camera's not broken, but a dangerous situation has just been created.
So what is this SOTIF thing, really? It stands for Safety of the Intended Functionality. And what that really means is making sure a system is safe even when it's doing exactly what you told it to do. It's all about being a detective, proactively finding and fixing those blind spots and limitations before they ever have a chance to cause a problem on the road. Okay, so you've got these potential risks. But when do engineers actually need to spring into action? Well, they don't just start fixing things randomly. They wait for specific clues or triggers that tell them it's time to open up a new case file and start investigating. And here's the thing, that case file can be thrown open at almost any point in the development process. A trigger could pop up super early, right in the design phase, when a computer simulation reveals a potential weakness. Or it could happen smack in the middle of testing, when a car fails a real-world challenge or uncovers a brand new hazard nobody even thought of. And sometimes it happens right at the finish line, when a final safety review says, nope, the risk here is still too high, we can't release this to the public.
And here is a fantastic real-world example of a trigger. Picture this. A car is driving itself. It exits a dark tunnel, and bam! It's hit with bright, blinding sunlight. For 3 whole seconds, its cameras are essentially useless. In that time, it could easily drift out of its lane. Now remember, nothing is broken. That's just a predictable limitation of a camera. But that risk? It's completely unacceptable, and that discovery triggers immediate, decisive action.
So, once a risk has been triggered, what's the plan? Our safety detectives have a big decision to make. Do they try to avoid the risk altogether, or do they mitigate it? This is a really important choice, and it comes down to 2 core strategies.
On one hand, you've got avoidance. This is always goal number 1. It means you change the system's design to completely eliminate the root cause of the problem. You make it so the hazard just can't happen in the first place. That's how you get an inherently safe design. But sometimes you just can't get rid of a risk completely, and that's where mitigation comes in. This is the backup plan. It's all about making the risk less likely to happen or making the consequences less severe if it does.
And this quote just sums up the whole philosophy perfectly. If you can't eliminate the risk, you must confine it to a manageable level. Mitigation is all about being a realist. It's accepting that absolute perfection might be out of reach, but then being absolutely relentless in controlling any risk that's left over, boxing it in so that even the worst-case scenario is survivable.
But of course, every good detective story needs a twist, right? Well, here it is. Sometimes the fix for one problem ends up creating a totally new one. For instance, say you want to make sure your car never misses a pedestrian. So you crank up the sensitivity on the sensors. But now the system might see a plastic bag blowing across the road, think it's a person, and slam on the brakes, potentially causing a rear-ended collision. It's this constant balancing act where every single action could have an unexpected side effect.
So to pull off these strategies without accidentally making things worse, engineers don't just guess. They have a structured safety toolkit they can turn to. It's a very methodical approach, and it's built around 4 specific categories of solutions.
Okay, let's look at the 4 main tools in this kit. First up, you've got system modification. This is straightforward. Just make the tech better, like putting in a more advanced camera. Second, functional restriction. This means you limit when the system is allowed to work, like automatically shutting off autonomous mode in a heavy downpour. Third, handing over authority. This is about getting the human driver back in the loop with really clear alerts. Lights, sounds, seat vibrations, you name it. And finally, there's addressing misuse, which means using tech like a camera that watches the driver to prevent us humans from making a mistake.
And let's just zoom in on that first one, system modification, for a second. This isn't just one simple fix, it's a whole world of possibilities. It could mean upgrading the hardware, like adding LiDAR to see things a camera can't. It could mean adding more kinds of sensors, like radar and cameras, so they can cross-check each other in fog. Or it could be all about the software, writing smarter algorithms that make better decisions with the data they already have. It's all about making the system's core ability to see and understand the world fundamentally better.
This brings us to the final, and maybe the most important piece of the puzzle. In the world of SOTIF, the case is never truly closed. This isn't about finding one problem, applying one fix, and then stamping the file solved. No, it's about a continuous, never-ending cycle of improvement.
And this is what that relentless safety loop looks like. First, you act. You implement one of the fixes from the toolkit. Then you update the official design document so everyone's on the same page. Next, you have to reanalyze the entire system from top to bottom, hunting for any leftover risks or, crucially, any new risks you might have created. And finally, you verify everything with brutal, intense testing. If you find a single failure at any point, well, you go right back to the beginning and the whole loop starts over.
So you might be asking, when does this cycle ever end? It only stops when two incredibly tough conditions are met. One, every single known risk has been proven to be at an acceptable, manageable level. And two, the entire safety case, the full story of your detective work, is formally signed off on and approved. It is an incredibly high bar for any system to clear, and frankly, it should be. Which really leaves us with one last, big thought to chew on. As these autonomous systems get more and more complex, as they become capable of handling almost any situation, is perfect safety a real destination we can one day arrive at? Or is it more like the horizon, something we'll be chasing forever? It seems the work of the SOTF detective is truly never done.